As we speak, there are two places in the world with the exact same temperature and pressure. This interesting result is obtained from an important topological theorem called the Borsuk Ulam Theorem. Proved in 1933, Borsuk Ulam Theorem states that for every continuous map F from Sn to Rn, where Sn is an n-dimensional unit sphere, there exists an x element of Sn such that f of x is equal to f of minus x. The theorem finds its applications in fields like differential equations, discrete mathematics, and economics. Today, our plan of action will be to briefly explain the proof for n equal to 1, focus on the proof for n equal to 2, and give an intuition for a general n where n is greater than or equal to 2. Before we begin the proof for n equal to 1, let us look at the terminologies. Antipodal or opposite points are diametrically opposite points on a sphere. Let us consider a one-dimensional sphere. A one-dimensional unit sphere is a unit circle since every point on the unit circle can be located accurately using just one parameter, theta. As we all know, theta is the angle made with respect to the x-axis. And for the three-dimensional sphere, which is the two-dimensional unit sphere, the points where the diameter cuts the sphere will give you the antipodal points, which are marked here by blue. For n equal to 1, we define a function g from S1 to R such that g of x is equal to f of x minus f of minus x. By algebra of continuous functions, g is continuous. We also get the g of minus x is equal to minus of g of x. If g of x happens to be 0 for some x0 element of S1, then we get that f of x0 is equal to f of minus of x0, which is what we wanted to prove. Otherwise, we'll get that 0 lies somewhere between g of x and g of minus x since they are negatives of each other. Since S1 is connected and R is ordered, we can apply intermediate value theorem. By intermediate value theorem, there exists an x0 element of S1 such that g of x0 is equal to 0. And therefore, f of x0 will be equal to f of minus x0. Since the proof for n equal to 2 is much less intuitive, it requires some terminologies. So brace yourselves and take notes if needed. For a topological space X, a path is a continuous map gamma from 0, 1 to X. Look at figure 1, where gamma of 0 marks the initial point and gamma of 1 marks the final point. Note that this is a map and not a function, so it need not pass the vertical line test. A path is a loop if gamma of 0 is equal to gamma of 1, which is precisely what figure 2 is. Moving on to homotopy, two functions from one topological space to another are homotopic if one of them can be continuously deformed, that is deformed without cutting, puncturing, or creating any holes in it, into the other. This particular deformation is what we call as homotopy. Imagine the solid line G and the dotted line F. As we vary the second parameter, imagine the solid curve slowly falling onto the dotted curve. That is, with change of time, one can imagine G slowly falling onto F, which means that these two curves are homotopic. Formally defining our intuition, small f is homotopic to G if there is a homotopy, capital F, from x cross the closed interval 0 to 1 to y with capital F of x0 equal to small f of x and capital F of x1 is g of x. Capital F can be seen as a path with small f of x and g of x as the initial and final points in some sense. A continuous map is null homotopic if it is homotopic to a constant map. Take the given loop based at the origin. If we include the interior of the loop, the whole of figure 4 can be squished to the origin, which is the darkened point. Here, we define capital F of xt as 1 minus t into f of x, where we get the initial point as small f of x, which is 0, and the final point as 0, since 1 minus t is 0 for t equal to 1. And hence we get that f is homotopic to 0. So small f is homotopic to 0, which is a constant map. Fundamental group of circles. Let P be the map from real numbers to S1, which is the one-dimensional sphere where T gets mapped to e raised to 2 pi it. Lifting of a map. Let H from some set A to S1 be a map. Lift of H is a map H tilde from A to the real numbers such that H is equal to P composed with H tilde. Since we are handling circles, the lift can be viewed as a map to the real numbers such that it takes a point on a circle and maps it to an angle corresponding to that point, which is a real number. Since S1 contains points only on the circumference, there are holes in the domain and it isn't simply connected. Homotopy is an equivalence relation, so each homotopy class comprises all loops that bind around the circle. The direction of binding determines the sign of the loop. Look at the figure for direction of binding and sign. Anti-clockwise direction will have positive sign and the clockwise direction will have negative sign. Let us now look at the figure with binary operations. Note, each blue circle represents a winding. To avoid confusion, we avoided the usual representation. Just remember that the whole thing is one loop and the different circles are the various windings. Imagine using a wire to wind a loop around a circle in the anti-clockwise direction once, which gives us -1. Now think of winding the same wire in the anti-clockwise direction thrice. The net effect is a loop that winds 2 times in anti-clockwise direction. In general, product of a loop that winds n times and a loop that winds m times is a loop that winds n plus m times. On a closer look, we can understand that the fundamental group of circles pi of S1 is isomorphic to the abelian group of integers under addition. We call Borsuk Ulam Theorem for n equal to 2, where a continuous f from S2 to R2 has no x in S2 such that f of x is equal to f of minus x. We plan to prove this by contradiction. Supposing there is no x in S2 satisfying f of x equal to f of minus x. We define a g from S2 to S1 and normalize. Now, g of minus x will be equal to g of minus of g of x. We get this from some very simple manipulations. Let eta be an equatorial loop from closed 0, 1 to S2 with eta of s equal to cos 2 pi s, sin 2 pi s and 0. The plot on the right side shows the brown colored equatorial loop of a unit sphere, which is kind of pink in color. For all s element of closed 0, 1 by 2, we get eta of s plus 1 by 2 as negative of eta of s. Using the trigonometric expansions of cos of a plus b and sin of a plus b, we get this particular equality. We choose this interval for s so that s plus 1 by 2 remains in our domain, which is 0, 1 by 2, the closed interval forming those two, with those two numbers as bounds. Define h as the composed loop of g with eta. From the previous equations, we get h of s plus 1 by 2 is equal to minus of h of s. Look at the figure on the right. This is our equatorial loop. The antipodal points on S1 are negations of each other, which is z1 is equal to minus of z2. From our understanding of complex numbers, the argument of the two antipodal points differ by an odd integer multiple of pi, which we can rewrite as 2 pi into n plus 1 by 2. Remember this n plus 1 by 2. Take the inverse of the map P we previously defined. Real numbers T1 and T2, which are pre-images of antipode points under P, differ by n plus 1 by 2, which we took note of earlier. This n plus 1 by 2 can be rewritten as q by 2 for some odd integer q. Let h tilde be a lifting of the map H. Let us lift takes a point on the circle and maps it to a real number corresponding to that point. H tilde of s plus 1 by 2 can be rewritten as h tilde of s plus q by 2. Now we look at h tilde of 1. Since 1 equal to 1 by 2 plus 1 by 2, we can rewrite it as h tilde of 1 by 2 plus q by 2. Since 1 by 2 is equal to 0 plus 1 by 2, we can again write this as h tilde of 0 plus q for an odd integer q.
Let's look at this map which goes from close interval I to S1 and we have named it H. We have previously seen as to why Q is odd, as well as we have gone through the lifts in the path in the previous slides. So now suppose if Q were even, more precisely if Q was 0, then we could lift the path to a 0 loop and that would have given us a null homotopy. But since Q is odd here, the path will get lifted to a non-trivial loop. Thus, we won't get a null homotopy. Now we look at the composition of G composed with eta and we'll study each individual map and check whether they are null homotopic or not. So, eta T is a homotopy, that is a continuous map going from I cross I to S2. Now, we'll understand as to why we are using this I cross I. So, let's come to a square, which is nothing but close interval 0, 1 cross close interval 0, 1. Now suppose if we fix a particular T naught on this square, T naught on this side of the square, then what does it actually mean? Then this T is equal to T naught indicates us to a particular loop from this family of loops that we see here, and S, the parameter S, takes us along the curve which takes us along the loop which we have named T is equal to T naught. So now let's look at the map. The map is described as follows. So we put the value of T as 0 and we see that we get our map eta S which was described previously, and for T is equal to 1 we get this constant, that is 0, 0, 1, and so we see here that this homotopy is getting mapped to a constant. Therefore, eta T is a null homotopy. Now let's look at the map G, which goes from S1 to S2. Before figuring out whether this map is null homotopic or not, we have certain questions that we need to answer. So yes, is S2 path connected or not is our first question. So as we have seen in the path connectedness section of Munch's, that this indeed is path connected, because for n is more than 1, you can take this map G, which goes from the punctured Euclidean space to Sn minus 1, and this map is defined by x by norm x. Clearly this map is continuous and surjective. Also, the continuous image of a path connected space is path connected, which forces our S to the power n minus 1 to be path connected. But let's just look into why this punctured space is path connected. So if you take like 2 points x and y on this punctured Euclidean space such that their path between them does not pass to the origin, then you can simply draw a straight line. But suppose if it were to pass to the origin, then we take a point z which does not lie on this path, and we connect xz and zy to get a new path. So any which ways, our s to the power n minus 1 is path connected as well. So now we have to see whether this S2 is simply connected or not. So a space is simply connected if first it is path connected and any loop on its surface can be continuously shrunken to a point. Going back to our S2, we take this loop gamma on it and we continuously shrink it till we get a point on it. So we see that S2 is simply connected because we have previously proven that it is path connected as well. So we use this proposition that for a path connected space X, if my X is simply connected, then I can have a continuous map F which goes from S1 to X, and this map is null homotopic. So we can use the point 2 in our given case and say that G going from S1 to S2 is null homotopic. So the composition of two null homotopic maps should be null homotopic. Hence G composed with eta should be null homotopic as well. But we have also previously proven that my map H is not null homotopic, and H was nothing but the composition G composed with eta. So we reach a contradiction here.
We have previously examined the Borsuk Ulam Theorem for the n is equal to 2 case. Now we'll try to look at it for any n greater than equal to 0. So for that we'll require these two equivalent statements, which are if I take a map F going from Sn to Rn such that there is a point x belonging to Sn and fx is equal to f of minus x. The point 2 is that the function f, which is antipodal, will have a 0. So we'll be starting with a contradiction. That is, we'll assume that we'll assume that f has no 0, and by the end of the proof we will show that we end up in a contradiction. So let's start with the proof. So f is a map from n-dimensional sphere to Rn, and now let's describe the map f a bit in detail. So this map f is sufficiently generic. Then this map f has no zeros, and it is a continuous antipodal map. Now we take another map G, which goes from Sn to Rn, and this is just a projective map. And so what happens in the map is that you take some point x belonging to Rn plus 1 and you project it to Rn. So naturally the zeros of this map G will be the north and the south pole. So a description of G will be that G is a non-constant map and G has two zeros. Now before we proceed further into the proof, we have to kind of understand what is a manifold and why is S1 a manifold. So a manifold is a space which is second countable, it is Hausdorff, and it is C infinite compatible. So S1, as we have seen, is second countable, it has a countable basis, and it's Hausdorff as well. So now we'll look into as to why it is C infinite compatible. So we take a unit circle and we look at the open sets on it. So u1 and u2 are open sets which cover the unit circle, and so are u3 and u4. So this phi 1 is basically a homeomorphism which takes my points on u1 to the x-axis, that is the interval on the x-axis, which is -1, 1, and that is true for my phi 3 and phi 4, just that it is projecting it to the y-axis on the interval -1 to 1. So before we go into describing what C infinite compatible means, we have to understand what exactly charts are. So if I take a topological space M, which is locally Euclidean, such that its dimension is n, then every point P on this M has a neighborhood U, which is which such that there is a homeomorphism phi from U to some open subset of Rn. So this pair of this open neighborhood U and phi is what we call as charts. So I take two charts, uh, U and U alpha and V beta of some topological manifold, and we see that they are compatible if these maps, composition maps, are compatible. So now we go back to our S1 case, and we take these intersection, that is we take our intersection of open set U1 intersected with U3, and we just take this composition map and see if the result that we get is C infinite compatible or not. So phi 1 inverse x will just map us back to the point x and root 1 minus x square, which lies on u1, and phi 3 will project it down to the y-axis. So thus we get root 1 minus x square, which is C infinite compatible. We do the same thing for u2 intersected with u4, and we see that it is C infinite compatible as well. So now we have to define something else, which is atlas. So this collection of these charts that we see, they cover M, and that is why my M can be written as the union of all these open neighborhoods. Thus the collection of my charts, that is in this case ui equipped with the homeomorphism phi I, is an atlas on S1. Thus S1 is a manifold. So this next proposition in simple words just means that if I have like two atlases for M and N, such that such that there is an atlas on the product as well, then this product M cross N is a manifold as well. So we see that the product of manifold is also a manifold. In particular, product of n manifolds. Now we look at X, which is nothing but my Sn cross the interval I. Now we describe a mapping F which goes from this X to Rn, and it's given by 1 minus tgx plus tfx. So this is, in a way, it's trying to connect my two spheres, fx, the sphere in fx and the sphere in gx. So what is the antipodality on Sn is extended via this map, a V. So what we do is that we keep our t fixed, and we take a point x and we map it to minus x. So what we do now is that we introduce this map V in our capital F map. So so now my capital F Vxt will map to minus Fxt. So now let us again recall a fact that F small f map had no zeros. Now what we are interested in is the inverse image of 0 under this map capital F. So what will the 0 belonging to Rn be mapped to in this X? We look at the rank nullity theorem, which talks about the dimension of rank plus dimension of nullity being the dimension of the entire space. So my rank here, that is the dimension of my image, is Rn here, but the dimension of the whole space is n plus 1. So the dimension of nullity should be 1. Basically, the dimension of nullity is nothing but the dimension of my zero set z. So z is a subset of my Sn, and as we know that Sn is a manifold and Sn is compact as well, we say that this Z is a one-dimensional compact manifold. So for a one-dimensional compact manifold, its components are paths and loops. So now we'll look into that. So I put my t as 0 and I'm projected to the lower sphere, which has a function g of x on this. Like so this is the figure that we get. So this map fxt will connect these two spheres, that is the lower and the upper sphere. So suppose if I put my t as 1, so I get 0 here and I'm mapped to fx. So this t is basically just a parameter which kind of gives it a height. Like, so this is like a hollow cylinder, and varying the parameter just takes our cross sections up. So now we'll look at 3 cases that are possible. So now my first case is, if I start with a path whose one endpoint is the north pole on the lower sphere, which has the function g on it, then will it go to any point on this cylinder? Like, is that a possibility? So the answer to that is no, because this path on this point, north pole, is on the boundary. So a boundary should be mapped to a boundary, since this is a continuous function. So this is not a possibility. Now we'll go to the next possibility. Now we look at a second case. As I've said previously that since this map is continuous, it will map a boundary to the boundary. So we take this point north pole on the boundary of my lower sphere and consider that this path goes to the south pole, which is again on the boundary of the same lower sphere. Though the other possibility could have been that my north pole would go to some point here on the boundary of the upper sphere, but we'll examine that case after this. So now this capital F map, capital F xt map, will get its characteristic of being antipodal because of the map small v of xt, because of which this map gx would be antipodal. Now what does this antipodal map actually do? So this antipodal map will map my north pole to the south pole and the south pole to the north pole, and because of which a loop will be created. Now the loop would be tangent, as it is just touching my sphere, and hence would increase the multiplicity of 0. So the formation of loop has increased the number of zeros that are present on this lower sphere. But we see this is a contradiction, because we had assumed that the function g had only 2 zeros, that is the north and the south pole. So now we'll further look into the third case. Now what we do is that we take the north pole and draw a path to some point here in our upper sphere, such that this point lies on the boundary. So we can have such a path because it's mapping a boundary to a boundary. But now we see that if I consider this point, this the end point of my path lying on fx, which will mean that my fx has a 0. So we are contradicting our assumption that f doesn't have a 0. Now since now we know that f has a 0, we'll go back to our equivalent statements. So Now we have seen this statement B being applied here. So now we know that our f has a 0. Now we construct the function fx such that it is hx minus h of minus x, and since there is a 0, this will be equal to 0. So we get this this statement A. Thus we prove that thus we come to a conclusion about the Borsuk Ulam theorem in n dimension case.
So there is a small confusion in this part of the proof where I talk about the north pole of the lower sphere going to the boundary of the upper sphere. So what I mean is that the zero of this map would get mapped to the zero of this. So basically, the north pole on the lower sphere would get mapped to the south pole of the upper sphere or the north pole of the upper sphere. So that's one clarification that I wanted to make, and because of which we see that my function f has a 0, and thus we come to the equivalent statement of our theorem.